Вернее, 5 минут, как мы ругаемся на то, что ничего не работает.
Ну не.
Там пока ничего нет.
Не, пока ничего нет, вот сейчас я запустил. Вы в эфире.
О, мы в эфире? Правда, что ли?
Да.
А что-то пока все равно ничего не видно. А, вот, отлично.
Да.
Nice. So, today's lecture is more in a festive spirit because today's topic is kind of a bonus topic for the course because it's not in the problem sets and not in the exam, but it is still quite interesting. So, what I want to discuss today are sums with primes and 3 primes theorem. So first of all, suppose you have some function f from natural numbers to complex numbers, and consider the following sum over all n less than or equal to capital N, lambda of n multiplied by f of n. Lambda is, as usual, the von Mangold function. And sometimes you would like to understand the behavior of this function. For example, if you take f of n to be identically equal to 1, this is the same as asking to estimate the number of primes below n, right? And if you take, say, so this is prime number theorem, if you take f of n to be some Dirichlet character, this is prime number theorem in arithmetic progressions, right? And if you take f of n to be lambda of n plus 2, say, then estimation of this sum is basically twin prime conjecture. Right, so it's basically a question of whether or not there are primes with difference exactly 2. But we are going to take a different case. In our case, f of n will have an oscillatory behavior. What I mean by this, I mean that we will take a function that looks something like this, maybe some sine or cosine, yeah, and then we will try to understand the behavior of this sum. So these two cases, they reduce to zeros of zeta of s and L as chi correspondingly, right? Well, if our function does not oscillate that much, then basically the question about the behavior of the sum is the same as the question for f of n identically equal to 1, right? For example, if you take something like f of n is equal to 1 over n log n, then what is it? What can be said about sum over all n lambda of n f of n? Can someone please tell me? So if n is prime, what is lambda of n multiplied by f of n?
It's 1 divided by 1 over n.
1 over p, yeah. So you get this is sum over all p less than or equal to n, 1 over p plus big O of 1, because the contribution of squares is small. So you get log n plus big O of 1, which is expected because the integral of 1 over n log n is precisely the double logarithm. And if you take, say, 1 over n log n, then you're going to get a triple logarithm and so on, right? Okay, so we are going to deal with the function f, which shows some oscillatory behavior, something like this, and let me formulate the first non-trivial step in today's discussion. It is not only the first non-trivial step, it is the main one. Lemma 1 is Vinogradov's identity in the form by Von. So let U and V be greater than or equal to 1. Then we have the following identity. Lambda of n is equal to A of n plus B of n plus C of n plus D of n, and A, B, C, and D will be the following functions. A of n will be just lambda of n multiplied by indicator function of n being less than or equal to U. Okay, so this is basically a cutoff of the von Mangold function. And B of n will be minus sum over all m times d times r is equal to n, m less than or equal to u, and d less than or equal to v, lambda of m, mu of d. So at the first sight, this will be incredibly unhelpful. 1 of n less than or equal to u. So it is equal to 1 if n is less than or equal to u, and 0 otherwise. Yeah. Then you have the second sum like this, and it should give you a feeling that this will be unhelpful because you have von Mangold function inside the formula for von Mangold function, but we will see that this is actually totally okay. Now C of n will be equal to sum over all md equals n mu of d mu of d log m, and d is less than or equal to v. And finally, d of n will be equal to minus sum over all mk equals n, m greater than u, k greater than 1, lambda of m, and then sum over all d dividing k, d less than or equal to v, mu of d. Okay?
D of n is sum over mdr equals m?
Yeah.
And where is r in?
R is not in the sum, so it's basically md dividing n.
Ah, okay.
Okay, so you can assume that for r you multiply every summand by 1, so you don't do anything. Okay? So this is the formula. We are going to use this formula in a very straightforward manner, but first let us prove it. Proof goes as follows. Take f of s to be sum over all m less than or equal to u, lambda of m to the power minus s, g of s to be sum over all d less than or equal to v, mu of d, d to the power minus s. Okay? So consider the following finite Dirichlet polynomials. Then we have the following obvious identity. Minus zeta prime over zeta of s minus f of s multiplied by 1 minus zeta of s g of s. Take this and then open up the brackets. What you're going to get? So you're going to get minus zeta prime over zeta of s. Then you're going to get minus f of s. Then you get plus zeta prime of s g of s, and then you get zeta of s f of s g of s. Okay? Right? Then what we're going to do with this one? Well, you see, this series here is equal to sum over all m greater than u, lambda of m, m to the power minus s, right? Because you take a cutoff of your function and you subtract it from the whole generating series.
Это первая скобочка вся, да?
Yes, it's the first bracket. And the second one is what? I think I've missed something or not. Sorry for that. The first thing on the left should be d. Basically, should be d of n. Yeah, of course. So what you get here is 1 minus what? Minus sum over all n, sums over all d dividing n, d at most v, mu of d, right? Correct? And then if you take a convolution of these two series, you are going to get precisely d of n, right? Because you get lambda of m from the first one. You get k greater than 1 because you subtracted 1. And you also get sum over all divisors dividing k, d less than or equal to v, right? So this thing on the left is precisely sum of d of n to the power minus s. Correct? Is this clear?
Цыганщина какая-то.
Вы пока ничего не видели. Сейчас вы увидите, что дальше будет происходить. Okay, so this is sum of lambda of n to the power minus s. This one, f of s, is precisely minus sum a of n to the power minus s, right? By definition. The third one is what? If you take a derivative of zeta, you are going to get minus log. And so this one is minus sum c of n to the power minus s. Right? And this one is minus sum b of n to the power minus s. And then you compare the coefficients in the identity, and you get that lambda is a plus b plus c plus
Сейчас
a.
f от n. Мы как взяли большое? Еще раз.
F от s,
Взяли?
вы имеете в виду?
Да, f от s сейчас.
Сумма по m непроисходящим u, лямбда от m на m в минус s. И это то же самое, что сумма a от n на n в степени минус s.
Сейчас.
Потому что это такая обрезка Мангольта. В точности она.
Сейчас, тогда... ладно, мы вам поверим.
It's just a trivial combinatorial check. Okay, so this concludes the proof of lemma 1. What we are going to do now is as follows. Take f of n, arbitrary function. And assume that f of n is less than or equal to 1. So we need some bound for f. Okay? So take an arbitrary function f of n and then sum over all n less than or equal to n, f of n lambda of n. The thing,
Это у нас...
what?
Arbitrary это у нас...
Произвольно. Okay, so then sum f of n multiplied by lambda of n is equal to sum over all n less than or equal to n, a of n plus b of n plus c of n plus d of n multiplied by lambda of n. Then you split this into 4 different sums. Okay? So you get S1 plus S2 plus S3 plus S4, and these 4 different sums will have kind of a different structure to them.
Секундочку. Может, у нас все-таки сумма там на f от n?
Of course. Sorry about this. F of n. Yes, this is an issue of non-commutativity in my writing. Okay, so you get 4 different sums, and they will have a different nature. So S1 will be kind of a short sum, S2 and S3 will be linear in some sense, and S4 will be bilinear. And we are going to see everything here. Okay. So we denoted everything by S1, S2, S3, and S4. Now S1 is the short sum, and the estimate for the short sum will be an obvious one, as usual. So absolute value of S1 is equal to absolute value of sum of all n less than or equal to u, f of n, lambda of n, right? Because a of n is just a cutoff of your function. But this is at most sum over all n less than or equal to u lambda of n, and this is of order at most u. So this concludes the estimation of S1.
This requires something about f. Okay.
Just about. Now let us estimate S2. So we know that the sum over all d dividing n lambda of d is equal to what? You should know this, by the way. This is actually equal to logarithm of n. And so S2, what is S2? S2 is equal to minus sum over all, let me show you. So here you have MDR is equal to n. M is at most u, d is at most v. Yeah? Then we group together terms with the same value of md. And we denote md by t. Okay? So let me rewrite what I wanted to say. So this is t at most uv, sum over all md is equal to t, mu of d, lambda of m, m is at most u, d is at most v, and then in the inner sum you get sum over all r less than or equal to n over t, f of rt. Okay? So what I did here is mdr is equal to n, md is equal to t, and n is equal to tr. Here is f of n. Yeah? Сейчас. Извините, значит, одну секунду. Хорошо, значит, вам лет такое, сейчас я вам покажу. Sorry for that. Okay, sorry for the necessary pause. Okay, so what do we do next? Next, we estimate this inner sum trivially. How do we estimate a sum like this trivially? Well, you see, sum over all md equals t, mu of d lambda of m is at most sum over all m dividing t lambda of m, right? This is obvious. And this is equal to log t, which is at most log uv. But we estimate everything very, very roughly, okay? So now you get that this is at most what? At most log uv multiplied by sum of all t less than or equal to uv, absolute value of sum over all r less than or equal to n over t, f of rt. Okay? So this is what I meant about the linearity of the sum S2. So what I meant is that we are going to estimate this sum S2 in terms of linear dilations of your sum. So you take f of rt instead of f of r, and then you sum it over the initial segment. Okay? Now we do the same with S3, but instead of doing like precisely this, we are going to creatively interpret logarithm. Okay? So S3 is equal to sum over all t less than or equal to v, mu of d, sum over all h less than or equal to n over d, f of dh log h. Let us compare this with the formula for Cn. I think this formula should be clear from this, right? For some reason, I denoted m by h, but I hope it's okay. So hd is equal to n, and then you get mu of d and log h, and d is at most v. Okay? Now, what? Now for the creative interpretation of logarithm. Logarithm is actually, as you might know, integral of dx over x, right? So let's write it as an integral of dx over x. So this is sum over d less than or equal to v, mu of d, sum over all n less than or equal to n over d, f of dh, and then integral from 1 to h, dx over x. Nothing happened, right? Now we are going to do what? Now we are going to do an insane thing. So we are used to shifting the order of summation. We are going to take the integral out, and then we are going to see what will happen. So this is equal to, well, h runs up to n, right? The maximal value of h is n. So you get integral from 1 to n. Then you get sum over all d less than or equal to v, mu of d, and then you get the following sum. Well, if your what? Here you get h, not n. Sorry. If your
It used to be n, but it's h. No, it's okay.
hd is equal to n.
Okay.
So it was never n. Okay. So if you have this integral and it contributes for fixed value of h, then you get h is at least x, right? Because this integral is from 1 to h. So h is at least x, and at most n over d, f of dh multiplied by dx over x. Correct? Then what? Well, for any d, for any fixed d, you can estimate this by a maximal value of your sum. So let me write down the estimate, and then you can agree with me or disagree with me. So this is at most log n multiplied by the sum over all d less than or equal to v, maximum over all x, sum over all h between x and n over d, f of dh. Correct? So for fixed d, you estimate mu of d by 1, then you estimate the integral by log n, and then you estimate the sum by its maximal value.
We need to take integral out to do this.
Yeah, of course, because why else do you get maximum of x? Okay, so so if you group this stuff together, you are going to get the following estimate. So this concludes the estimation of linear sum, two linear sums, and one short sum. And so you get S1 plus S2 plus S3 is at most U plus log n times sum over all t less than or equal to UV, maximum over all x, sum over all r greater than or equal to x, less than or equal to n over t, f of rt. Correct? So for the first sum you get u. For the second sum you get this, but I also added x inside the sum and took maximum value. And for the third sum I slightly widened the range of t. Okay, so you get this this estimate which works for all three terms. And now we have the final challenge, which is the bilinear sum. The bilinear sum is a bit of a fun one. So notice the following: that if you take u of n, which is equal to sum over all d dividing k, d less than or equal to v, mu of d, then u of n is equal to 0 if sorry, what is k? It's n, d dividing n. Sorry for that. So if you take this u of n, then u of n is equal to 0 if n is greater than 1 and less than or equal to v. Right? This is just a Möbius inversion formula. So this allows one to rewrite S4 as follows. S4 is equal to what? Let us look at the formula once again. So you get this stuff, m is greater than u, k is greater than 1. Then you have this sum, which is u of k, right? And then you have lambda of m. So the sum is basically mk. What have I done? Is this okay? Yeah, it's probably okay. Okay, so you get u of k here, and you get lambda of m here, right? So for S4, you get the following formula: sum over all m greater than u and less than or equal to n over v, and k greater than v and less than or equal to n over m, something like this. Then you get lambda of m, u of k, f of mk. And this is what I've meant about the bilinearity. You have two sets of coefficients, lambda and u, and you multiply it by f of mk, and then you need to somehow estimate this combined sum. Okay? So what we are going to get? Here I need you to accept one assumption, which we will prove next. Assume that for all B and C are sequences now. For all sequences B and C, and for all M between U and N over V, we have the following. Absolute value of sum over all M between capital M and 2 times capital M, and K between V and N over M, BM CK, F of MK. So suppose that this is at most delta sum of BM squared over all M between M and 2M to the power 1/2, sum over all K less than or equal to N over M, CK squared to the power 1/2. So this is kind of a quintessential estimate for the bilinear sum. So it is some constant multiplied by a product of norms. Okay? So if you have something like this, then using the using the dyadic subdivision of your interval, so you basically take this interval of values of M from U to N over V, and you subdivide it into intervals of the form from M to 2M, okay? Then you get the following, that S4 is at most delta log N. Log N is the number of intervals in your subdivision.
Log n or n?
What?
Log n or n?
Log N, of course, because you take a subdivision into intervals from M to 2M, right? And so you need just a logarithmic number of terms, correct? So maximum over all M between U and N over V of the following product. Sum over all M between M and 2M, lambda of M squared to the power 1/2 multiplied by the sum of all K less than or equal to N over M, U of K squared to the power 1/2. Okay? So this is just the same estimate, but for any dyadic interval, and then you get the maximum, right?
Еще раз, можете провод значение выяснить?
Мы предположили, что есть какая-нибудь константа дельта,
Всё.
так что вот такое выполнено. Понятно, что она какая-то есть, потому что, ну, как бы норма, там, не знаю, билинейной функции на конечномерном пространстве конечна. Okay. What do we get next? This is at most delta log n. Then what? Then you get m log m to the power 1/2. This is obvious because lambda of m is at most logarithm, so you can estimate this by lambda of m multiplied by logarithm, right? So you get m log m, and inside you get n over m, and then log cubed of m. I will not explain in details how do you get log cubed. I just tell you that u of k is at most the number of divisors, tau, and if you sum tau squared, you get log cubed. Okay, so then uniting everything together, you get delta square root of n times log cubed of n. Right? Еще раз, вопрос про куб логарифма или нет?
Пока нет. Но сейчас будет.
Просто все вместе выпишем, у нас все получится. Okay? Can I continue? Okay. So what is the trivial bound for your delta? Trivial bound for delta is you can just assume that f is 1 and then use something like Cauchy-Bunyakovsky-Schwarz like trivially, right? So the trivial bound for delta is square root of n. And we need something better than square root of n. Because if you substitute delta as square root of n, you get square root of n multiplied by square root of n multiplied by logarithm. This is worse than trivial. Okay, so let us use Cauchy-Bunyakovsky-Schwarz, but more creatively, okay? So sum over all m between m and 2m and k between v and n over m, bm ck f of mk is at most what? Let's look at this sum as sum of bm multiplied by some function of m. Yeah? So this is at most sum over m, I will not write the interval, bm squared to the power 1/2 multiplied by what? Multiplied by the following funny sum. Sum over all m between m and 2m, and then sum over all k between v and n over m, ck f of mk squared to the power 1/2, right? So this is just Cauchy-Bunyakovsky-Schwarz. Nothing more, nothing less. Yeah? Now what should we do? Well, now we should expand the brackets inside the last sum. Expanding the brackets, you are going to get what? Sum over all m between m and 2m. Sum over all k between v and n over m, ck f of mk squared. Then you multiply this sum by its conjugate. And expanding the brackets, you are going to get the following. Sum over all j and k between v and n over capital M. Then you get cj ck conjugate, sum over all m between m and 2m. Then m is at most n over j, m is at most n over k, f of mj, f of mk conjugate. Okay, so now this product is at most 1/2 of sum of squares, right? And so cj ck is at most cj squared plus ck squared. And so applying this, but I do not want to go into the details further, you get that delta is at most delta of FUV, which is the following very large sum. Maximum over all m greater than u, greater than or equal to u, and less than or equal to n over v. This is the definition. J between v and n over m. And then you get sum over all k between v and n over m. Sums over all m between capital M and double M. M is at most n over k, and at most n over j. F of mj, f of mk conjugate. And this all e to the power 1/2.
Так,
Okay?
можно немного времени на осознать, что тут вообще написано?
Значит, еще раз, по-русски. Значит, вы переписали неравенство Каши-Bunyakovского-Шварца один раз.
Нет, вот вопрос скорее именно того, что именно написано в плане, в прямом смысле, что написано, потому что половину времени за вами просто не было видно.
В смысле, дельту можно...
В смысле нет, в этой сумме. Вот пока вы писали, просто за вами не было видно, поэтому можно немного времени на осознать.
Хорошо. Okay, so let me formulate the estimate we've got. This will be lemma 2. Lemma 2 is as follows. So if f of n is at most 1, 1 is at most u at most v, qv is at most n, then we get the following. Sum of all n less than or equal to n, lambda of n, f of n, is at most u plus log n multiplied by the sum of all t less than or equal to uv, maximum over all x, sum over all r between x and n over t, f of rt, plus square root of n, delta fuv, log cubed of n. So this lemma is basically what we have proved already, right? So I've just compiled everything together. And what is the hope of all of this is that we assume that f is an oscillating function, and then we hope that all these sums will exhibit some cancellation. And let me show you the application. Я могу переключить, да? Let me show you the application of this result to the most obvious oscillating function ever. What is the most obvious oscillating function?
Sinus.
Yeah, something like this, complex exponent, right? So linear exponential sum with lambda of n. I will not go into much details about the estimate, but okay. So take f of n to be e to the power 2 pi I n alpha. Then you get the following theorem. If a and q are coprime, q is a natural number, and alpha minus a over q is less than 1 over less than or equal to 1 over q squared, then t of alpha, which is sum over all n less than or equal to n, lambda of n, e to the power 2 pi I n alpha, can be estimated as follows: n over square root of q plus n to the power 4 over 5 plus square root of nq multiplied by logarithm n to the power 7 halves. Okay? This
T of alpha is.
T of alpha is
It's just a.
exponential sum with von Mangold function. Okay, so this is non-trivial for q greater than logarithm n to the power 7 and q less than n over logarithm n to the power 7. So there is a very, very wide range of non-triviality here. Okay? Because, of course, the trivial bound is n, and these are the bounds where you get a slightly less trivial bound. Okay? So let me explain what we do here. Sum over all n between m and m plus k, e to the power 2 pi I n beta for any beta is at most minimum between k and distance from beta to the nearest integer to the power minus 1. This is a known estimate for the linear exponential sum. It is done by a formula for the geometric progression, right? Okay, so what do we get now? T of alpha, we are choosing choose UV such that the product is at most n. Then lemma 2 gives you T of alpha is less in order than U plus sum over all T less than or equal to UV, maximum over all X, sum over all R between X and N over T, e to the power 2 pi I RT alpha. So this is the linear sum you get. And then plus square root of n log cube of n delta FUV, right? Then you bound your stuff and you get the desired result. Let me show you the bound without much explanation, if it's possible. Okay, so sum over all T less than or equal to UV, all of this stuff is at most sum over all T less than or equal to UV, minimum of N over T, and the distance from T alpha to the nearest integer to the power minus 1. Yeah? So this is obvious. Then you write T as HQ plus R and write beta as alpha minus A over Q, which is small as we assumed. And then we split this sum into sums over residue classes. So T is at most UV, so H is at most UV over Q. So this is at most the following. Sum over all H between UV over Q and greater than or equal to 0, sum over all R from 1 to Q, and then minimum of N over HQ plus R, and the distance from the nearest integer to RA over Q plus HQ beta plus R beta to the power minus 1. Okay? So this is just substitution to here. And then if H is equal to 0, then the sum is, if H is equal to 0 and R is less than Q, then the sum is bounded by what? The inner sum, I mean. By Q log Q. Yeah, so this here you get Q log Q. This is what you get from the second summand. Because beta is small, beta is at most 1 over Q squared. And then you get this small addition, and so the distance from RA over Q plus R beta to the power minus 1 is basically what? Is basically Q over some integer, and this integer will be different for different values of R, and so you get you get sum of Q log Q. And if H is greater than 0, then you get estimate N over Q H plus 1. So for all of this, H greater than 0, you get N over Q H plus 1. And so you compile all this stuff together, and you get a bound N over Q plus UV plus Q plus log Q UV, or something like this. Okay? This is purely technical. And when you estimate the sum of the delta part, you get that delta squared of FUV is at most maximum over all m between u and n over m, m plus sum over all m between 1 and n over m, minimum of n over m, and 1 over distance from m alpha to the nearest integer. This is the same because in delta, let me show you, in delta,
It wasn't here, I think.
maybe here, yeah. In delta, you get this sum, and in case when f is your complex exponent, you once again get linear sum in m, right? So if you get a complex exponent, you get e to the 2 pi I alpha, and then mj minus mk. So you get complex exponent and sum over m. And so you still get a linear sum, and so everything goes well. And so this can be bounded by n over v plus n over u plus n over q plus q log qn. This is an exercise for a very, very interested listener. Just like complete the computation. And so you apply all of this for your T of alpha, and you get uv plus q plus n over square root of u plus n over square root of v plus n over square root of q plus square root of nq, and then you get log n to the power 7 over 2. And then you choose u equals v equals n to the power 2 over 5. And then you get the desired estimate. Okay? I hope you got anything from this, because now I want to apply this result. I want to apply this result to a certain very well-known problem. A very well-known problem is the Goldbach conjecture, which has two forms. The first form is that for any n greater than or equal to 2, there are primes p1 and p2 such that 2n is p1 plus p2. And the second form is that for any n greater than or equal to what? To like 3, there are primes p1, p2, and p3 such that 2n plus 1 is sum of 3 primes. So in other words, every large enough even number is the sum of 2 primes, and every large enough odd number is the sum of 3 primes. And what we are going to prove is the following theorem due to Ivan Matveyevich Vinogradov, which was proved in 1937. He proved that there is an n0 greater than 0, greater than 0 is of course unnecessary, such that for any n greater than n0, n odd, there are p1, p2, and p3 such that n is p1 plus p2 plus p3. What is remarkable about this result is that from its proof we will see that there is no way to estimate n0. No way at all. So this is completely ineffective. But the first explicit estimate for n0 is due to K. Borostkin, Konstantin, I guess, I don't know actually the name of this guy. So the first value for n0 is at most e to the power e to the power e to the power 41.96. This is due to K. Borostkin. And the result which is known today is that you can actually take n0 to be equal to 5. And this is due to Harald Hilfgott. A very cool mathematician from Peru.
So the Goldbach, the second part of Goldbach conjecture is proven?
You mean this one? Yeah, it is known to be true.
Ah, okay. And the first one is?
And the first one we don't know yet.
Ah, okay.
Maybe soon someone will find it defeated, but I doubt it, to be honest. Okay.
So n0 is actually a 3. Why is there a 3 and here is a 5?
Because 2 times 3 plus 1
okay.
is 7, right? Okay. So, as usual, instead of constructing the solutions, we are going to count them. And let us define R of n to be integral from 0 to 1. T of alpha, the same exponential sum, cubed e to the power minus 2 pi I n alpha, d alpha. This is what? This is sum over all a, b, and c less than or equal to n, lambda of a, lambda of b, lambda of c, multiplied by the integral from 0 to 1, e to the power 2 pi I, a plus b plus c minus n, alpha d alpha. Correct? This is just cubing the sum and expanding everything, right? So the inner integral is equal to 0 if the sum a plus b plus c is not equal to 1, to n, and 1 if it is equal to n. So this is actually sum over all a plus b plus c equals n, lambda of a, lambda of b, lambda of c. And we are going to prove that R of n is actually of order at least n. And if we are able, at least n squared, sorry, at least n squared. And if we are able to prove this, then we are of course able to prove the whole Goldbach conjecture, because if one of your variables is a square of a prime, then you get a smaller bound for the contribution. Okay?
The whole Goldbach conjecture.
What?
The whole Goldbach conjecture.
No, for large enough. If we prove something like this for large enough, and then you are going to get theorem 2, right? Because the contribution of squares, cubes, and so on it will be negligible, basically. This is a bit of a sloppy reasoning, but you can recover everything here. Okay, so now fix large A and B and set the following. Tau will be n over log n to the power A, and tau 0 will be log n to the power B. Okay? So this is kind of the same as the non-triviality interval for the estimate, right? So we are going to shift our integral by -1 over tau. So R of n is actually equal to integral from -1 over tau to 1 over tau, t of alpha cubed, e to the power 2 pi minus 2 pi I, and alpha d alpha. Yeah, this is due to periodicity. Okay, now we are going to define major arcs and minor arcs. Major arcs will be the following set. E1 will be the union over Q less than or equal to tau 0, union over all A and Q are co-prime, interval from A over Q minus 1 over Q tau, A to A over Q plus 1 over Q tau, and then E2 will be our interval of integration minus E1. This will be the major arcs, and this will be the minor arcs. And you are going to see what we are going to do. Okay, so R of n is of course equal to integral over E1 t of alpha cubed e to the power minus 2 pi I alpha n d alpha plus big O of integral over E2 t of alpha cubed d alpha. What is strange about this construction is that this set E2 is actually quite large compared to the set E1. But it turns out that the main contribution to the formula will come from E1.
How do we get this equality for R of n?
You see, your interval is a union, disjoint union of E1 and E2. And so for E1, you just write the integral,
Yes.
and for E2, you estimate everything trivially. Okay. Now for the bounds.
So we could have taken E1 to be even less hypothetically. We could have taken it to be very small.
E1 is already quite small.
Okay.
So tau naught is a power of logarithm.
Okay.
So E1 is the set of all numbers in your interval which are well approximated by fractions with very small denominators. Okay, so for any alpha in E2, there is a Q between tau naught and tau, and A and Q coprime, such that alpha minus A over Q is at most 1 over Q squared. This is just Dirichlet approximation theorem. Dirichlet approximation theorem gives you that for any alpha, there is a Q below tau such that the distance from alpha Q to the nearest integer is at most 1 over tau. And since your alpha is not in E1, this means that this Q is between tau naught and tau. And so you get this bound, okay? This is the Dirichlet approximation. Now what? We are going to estimate this integral very fast. So we are going to just use our theorem about linear exponential sums. So integral over E2 t of alpha cubed d alpha is at most supremum over all E2 t of alpha multiplied by the integral from 0 to 1 t of alpha squared d alpha. Now, can someone please tell me how can we estimate integral t of alpha squared? So I will not wait too much. So this is sum over all n less than or equal to n, lambda of n squared. And so this is at most n log n. Okay? So this is at most n log n. And for your t of alpha, you are going to get the following. Let me show you.
Logarithm squared probably, no?
No, just logarithm, because lambda of n squared is at most lambda of n multiplied by logarithm. And sum of lambda of n is at most n. But you can write logarithm squared. It will not do anything to your bound actually. Okay, so let me show you the bound. Подождите, давайте посмотрим на оценку. Видите, let's look at this bound. You get n over square root, and you get square root of nq. and you also get logarithm n to the power 7 halves. Let me show you what we get from this bound. So here we get n log n, and then we get n, and then we get logarithm n to the power minus half of a plus logarithm n to the power minus half of b times logarithm n to the power 7 halves. Okay? So if your a and b are large enough, the contribution of minor arcs will be at most n squared divided by some huge power of logarithm. Okay? So this is less than n squared log n to the power minus c for some huge constant c. Okay? Now we need to sum.
Там получается минус а пополам, плюс минус b пополам, плюс умножить на 7 вторых.
Да, и если а и b большие, то у нас получается все хорошо. Okay, so now we need to evaluate the contribution from the major arcs. I think I have like almost negative amount of time left, so let me do it very fast. So integral over e1 t of alpha cubed e to the minus 2 pi I and alpha d alpha will be sum over all q less than or equal to tau naught, sum over all a and q coprime, integral from minus 1 over q tau to 1 over q tau, t of z plus a over q cubed, e to the minus 2 pi I n a over q plus z dz. Okay? So this is just a rewriting of our formula for E1. Okay, so now we need to decide how does t of z plus a over q behaves when z is small. And there is a following formula. T of z plus a over q is sum over all b and q coprime e to the power 2 pi I ab over q multiplied by the sum over all n less than or equal to n congruent to b modulo q, lambda of n e to the power 2 pi I and z, plus some small correction coming from n not coprime to q. Okay? Is this formula clear? So you write this as a sum of lambda of n multiplied by exponent, and then you split the sum into residue classes modulo q. And so you get outside you get some oscillating exponent, and inside you get exponent of something very small. Okay, so now sum over all n less than or equal to n congruent to b modulo q, lambda of n e to the power 2 pi I and z is equal to what? It is equal to psi of n qb minus e to the 2 pi I and z. This is just an integration by parts. 2 pi I z, integral from 0 to n, psi of x q b e to the power 2 pi I x z dx.
Psi is the sum of Mangold function.
Yeah. Psi is just the sum of Mangold function without exponent. Okay? So for this function, we have a formula from Siegel-Wallfisch theorem. Siegel-Wallfisch. Siegel-Wallfisch gives you that psi of x ql is equal to integer part of x divided by phi of q plus big O of x e to the minus c square root of log n if x is greater than or equal to square root of n. Okay? Here we used that q is at most a power of logarithm. Okay? So when you substitute, why do I need this integer part? I need this integer part so that I can substitute it back and replace lambda here with 1. So there is a formula, sum over all n less than or equal to n congruent to b modulo q, lambda of n, e to the power 2 pi I n z is equal to L of z divided by phi of q plus big O of n e to the power to the minus c log n, and L of z is actually just a linear sum. Okay? This is due to the use of the integer part here.
Сейчас я извиняюсь, а там в первой сумме, в последней строке, там что в показателе степени e?
2pi nz. Сработало? Then we substitute this formula back here, and so what you get is the following. You get t of z plus a over q is equal to sum of all p and q co-prime e to the power 2 pi I ab over q divided by phi of q multiplied by L of z and plus the error term. And it turns out that this sum here, it is called the Ramanujan sum. It is equal to mu of q divided by phi of q. So it is equal to mu of q divided by phi of q L of z plus big O of n e to the minus c log n.
The sum is equal to mu of q.
To mu of q, yeah, to Möbius function. And then you substitute everything back, and what you get is the following. You get that the integral from minus q tau, minus 1 over q tau to 1 over q tau, t of z plus a over q cubed, e to the minus 2 pi I n a over q plus z dz will be equal to mu of q divided by phi of q cubed multiplied by the integral of the linear exponential sum L of z cubed e to the power minus 2 pi I a over q plus z dz and plus some small remainder term like n squared c square root of log n. Okay? And so what do we get from this? You get so I would like to skip the rest of the computation if possible, because from this you get the following. You get that R of n is equal to sigma times gamma plus remainder term. Remainder term looks like n squared log n to some large power. And what is sigma and what is gamma? Sigma is what is called the singular series, and gamma is what is called a singular integral. The singular integral gamma is kind of an Archimedean contribution to your sum. E to the minus 2 pi I nz dz, and in this case this just evaluates to the number of a, b, and c such that a plus b plus c is equal to n. And this is of course equal to n squared over 2 plus big O of n. So the singular integral is very easily evaluated. And the singular sum, sigma, is equal to sum over all q, cq of n, mu of q over phi of q cubed. And CQ here is still the Ramanujan sum, which is CQ of n is sum over all a and q coprime e to the power 2 pi I a n over q. Sorry, not yeah, it's okay. Yeah, so you get this, and this turns out to be a multiplicative function, and so this singular series evaluates to the following product.
I thought this sum is equal to mu of q, no?
No, it is equal to mu of q only if a is coprime to q. N can be not coprime to q, and then you get not Möbius function, but something more interesting. And so this sum evaluates to something like this. Product of all primes dividing n, and product of all primes not dividing n. And this is of order at least 1. And so from this, you get certain formula for the function r, and so you get that r of n is equal to sigma n squared over 2 plus basically big O of n. No, I think you get something worse. You get n squared log n to the power minus c, but it's still okay. Okay, so this approach not only it detects the sums of 3 primes. Not only it proves that every large enough number is a sum, every large enough odd number is a sum of 3 primes. It also shows the following. It shows that if your number is divisible by a lot of primes, then, for example, it has less representations as sums of 3 primes as other numbers, correct? So, for example, you get some nice arithmetical insights from this proof. This is due to the appearing of this term, which is a product of primes. And this term is thought of as a non-Archimedean contribution to a sum. So this means that this is kind of a real part, and this is kind of a periodic part. Okay? So there is a trace kind of real numbers here and traces of periodic numbers. Okay? So that's it. Thank you for listening to the course, and have a good luck with your exam and all the other exams at the department, and Happy New Year.
Thank you.
Всегда спрашивают, а как вас зовут? Я задал вопрос, я уже ухожу, как вас зовут? Я сейчас
Нет, нормально. Типа...
Я не привык к таким вежливым людям в деканате. У нас там были такие, что зашел, и отчислен сразу.
Не, у нас, скажем так, на матфаке сильно проще.
Я это заметил.
Тебя наоборот стараются знать в лицо, чтобы в случае чего понимать, кто ты и как тебя искать.
Посмотри на меня, как ты думаешь, мне легче? Я за семестр постарел на 5 лет. Я уже не хочу изучать математику, между прочим, я хочу дальнобойщиком быть.
Блин.
Так, идет
Все-таки-
трансляция.
Да вот черт его знает, вроде нет. Там все время, там Kalmynin все заканчивается и заканчивается. В смысле, именно лекция.
О, пошла. Я тебя только что увидел.
Так, да, все,
Okay,
пошел.
today we'll finish, I will finish my talk about Lorentz problem. Let me remind you, big G of k is minimum n r such that every sufficiently large number, natural number, is the sum of r k powers. Here we prove for sufficiently large numbers, and the main theorem that we want to prove is that g of k is less or equal than 2 to the power k plus 1. And how we want to prove it? We want to find asymptotic expression for so let r of n be the number of representations of n as a sum of x1 to the power k plus x s to the power k, and for s greater or equal than 2 to the power k plus 1, we will find asymptotic expression, and from it will be clear that this number of representation is non-zero for n large enough. Okay, and so we introduced big N, it's n to the power 1 over k, and we looked at such series, exponential sum, n1 to big N, exponent, it's exponent of 2 pi multiplied by here alpha to n power k, and we know that r of n clearly it's integral from 0 to 1 f of alpha to the power s exponent minus alpha n di. Okay, so just quickly. And our aim is to estimate such integral. And for this, we introduced a major arcs. So let mu be 1 over 400. And major arc is like that. It's numbers in little neighborhood of a over q less or equal than n to the power nu minus k. So this is very small number, and m become large arcs. This is a union n to the power nu m q. So it's a union of small neighborhoods of with fractions with relatively small denominator. Yes, and I told you that we estimated it. Measure of this major arcs is relatively small, yes, but the main term will come from integral over this major arcs, and minor arcs is just yes, it's just the rest. And we had we estimate so in a previous lecture we estimated our integral over so this will be integral over major arcs for our function plus the same over minor arcs. Yes, the same. And we estimated this part. So we used, let me remind you, it was Weyer's inequality. we will use it once again today. So let me just remind you, it was the main tool to estimate it. It's like that. If alpha is near Q, phi of x is polynomial, and then such sum Q E of phi of x, we estimated it like that. Q 1 plus epsilon over big K, and big K is 2 to the power K minus 1. And we used this lemma, and the main theorem that we proved in the previous lecture, it was that theorem 1, that our integral over minor arcs actually integral with absolute value is small. It's less than n to the power is k minus 1 minus delta. And what we will, and now we will compute our integral over major arcs. And actually our integral over major arcs will be of order of such order, we will see. So this delta is some small number which depends on the small k. So we will. Okay, now let us start to compute it. So let us introduce some notation. V of beta will be such sum. Here is our n. Yes. And we will evaluate our integral with this v, and somehow we so here it's written that it's maybe interpreted like probability that m is K-club. And so we want to make our function in the integral smooth somehow. Yes. This is so there are several choices. Not only this function is nothing special about this function, but we will use it, and we will need such series. So it's like analog of Gauss sums, but for bigger power. Okay, and lemma 7 will be like that. So if we have our major arc, and alpha in this major arc, then our function f of alpha can be evaluated in terms of these two functions. F of alpha is q to the power minus 1 is a v of alpha minus a over q plus b of n to the power 2. So let's follow it. And So first, let us note that what's such sum. So y, if y is bigger than q, you see these terms are periodic. Yes, of course, with period q, at least. That's why it's 8r to the power k over q, and here will be sum of m less than y, m equal to r modulo q. Yes? And this is, we see that this we can evaluate like y over q plus bq of 1. Yes? And here we have our series. So this will be q to the power minus 1 sqa y plus bq of q. Okay? And what about such sum? 1 over k m 1 over k minus 1. See, the integral of such function is just y. Yes? So it's y plus bq of 1. And now we let us define C of m to be such function. So C of m will be difference of this and this somehow. SQA 1 over k m 1 over k minus 1 if m is k of power. And otherwise just that part. Okay? Otherwise. And we see that sum of Cm less than y to the power k, Cm, I think m, yes, m. It's less than q. Okay, just, so here, if m is k of power, we have here. So in total, this sum is this sum minus this sum. Yes, multiplied by this expression. Okay, and difference is bq of u. Do you agree?
Вопрос. У нас получается, мы говорим, что m это k-тая степень просто какого-то числа произвольного или простого обязательно.
Что еще раз? M?
Да, вот мы описываем тем, что у нас m это степень, это k-тая степень, мы подразумеваем, что m это k-тая степень простого или какого-то произвольного натурального.
Натурального. Ну вот, как здесь.
Ну вот просто на всякий случай уточняю.
Угу. Да. And from this, we deduce that hence sum. What is sum? yes, first write like that. And now it's very close to the sum that we want to estimate. Yes. I claim that this is, so we can integrate it by part, and then we'll see that this is less than like that. Okay, just integrate this by part. And from this, let's take x to be n and beta to be alpha minus a over q. And then 1 plus beta x multiplied by q is less than what? 1 plus, and what will be here? X is n, yes? Beta is less than n to the power u minus k, yes? By our definition of major arcs. And q is less than n to the power nu. And all of this is less than n to the power 2 nu. And this, if x is n and beta is alpha minus a over q, here will be essentially the difference of f of alpha and this expression. So there is nothing deep here, we just replaced our f of alpha with a more smooth function. Okay. Okay. How to delete page? Oh no. And so now we are interested with this function. Q to the power minus 1 is qa v of alpha minus a over q. And if alpha is in our major arc. And if we want to evaluate f of alpha to the power s minus this v of alpha q a to the power s, yes, we know that f is close to v in this arc. And what's the difference of s powers? It's less than this to the power s minus 1 multiplied by difference, yes. So f is bounded by n, and v also is bounded by n. Okay, and this is small, or how small? N s minus 1 plus 2 nu. And now, what's the integral over major arcs? It's such sum. Q is less than n to the power nu. A is O prime to Q. Integral A f5 power s, and let's evaluate the difference with this power minus v of alpha q a to the power x d alpha. It is less than so it will be our estimate, yes, first. How long is this arc? It's n to the power nu minus k, yes? Yes? This the length of the sum. And how many sums we have? N to the power minus q and a, so it will give us n to the power 2 nu. Yes? All such pairs. So with our estimate, and it's n to which power? N to the power s minus k minus 1 plus 5 nu less than n. I remind you that Bkn is n to the power 1 over k. Yes? So this is s over k minus 1 minus some small number. And again we have the remainder term as small as the previous one. That's why we can work now with our new function. So yes, so we proved that f of alpha to the power s minus alpha and d alpha, let's write from 0 to 1, is some, let's denote it as star of n plus bq of n, so k minus 1 minus delta, and r star of n is such sum. So it's integral over major arcs of our v alpha q a to the power s exponent minus alpha n d alpha. And the claim is that we can decompose this in a product like that. Let me first write product of what, and when we will see that this is true immediately. Claim, so some other notation, n nu g star n. Here g n q is such sum. So here will be our SQA, and with the definition, I remind you, to the power s, exponent of minus an over q, and g star will be integral from minus n nu minus k n nu minus k v beta to the power s exponent minus beta n d beta. Okay, and how can we see it? Just change variables beta, let beta be alpha minus a over n. Okay, if we make such change in this integral, yes, v is like that. Yes, if this will be v of beta, and it will be just we can decompose it as a product, yes, because variables are independent. Okay, do you see it? And here we will see that
Is S
S это в какой степени?
S of Q,
Где?
what the definition?
Ага, это вот можно вот из V посмотреть, просто ну, здесь есть, даже не важно что для этого приложения. Ну вот это наша сумма такая. And we will see that this is like the volume, real volume of our equation, that's sum of k powers is n. And this somehow correspond to its periodic behavior. Now we want to compute these two terms. First, let us note that SQA, yes? Again, what is it? SQA is such sum. And we can apply Weyer's inequality, yes, because it's exponent of polynomial. And so let me just write it. You can Weyer's inequality, yes? You apply Weyer's inequality and you see that it is less than q to the power 1 plus epsilon minus 1 over bk. Epsilon is arbitrarily small. So just apply Weyer's inequality and you will see that. And let us denote this part by S of q. Okay? No, not this part. I need different color, I think. А где у нас цвета? О. Я хотел вот так сделать. Okay, this will be S of q.
Not black, probably. Not black, probably.
Что?
Белый цвет выбрать.
White color.
Что?
Вы выбрали цвет черный.
Ну я бы это понял. Ну хорошо. Спасибо. And hence, what is SQ? SQ is so this to the power s, yes, and also sum over q. SQ is less than this to the power s. It will be q epsilon. Yes, and also multiply by q to the power minus 1. So this will be epsilon minus 1 over bk to the power s. And also there are
Сейчас, а там интересно малое К или большое К?
где?
Вот.
Большое К, да.
К большое, это которое
2 в степени К минус 1. Ну, там, да. Ну, оно не... Да, большое, но не очень.
Ну,
Ну, в смысле,
большое в смысле,
мы сделаем, может...
большое в смысле именно строчный или
Да.
заглавный.
And I claim that S is bigger than 2 to the power k plus 1, as you remember, yes? So this is less than q to the power minus 1 minus 2 to the power minus k. Here is small.
Сейчас. Тогда вопрос, а раньше тоже везде у нас были К большие? Или...
Где? Нет, это К маленький везде.
То есть сейчас у нас...
Только вот здесь К большой.
Ну да, здесь у нас вот только здесь в степенях появились К
Да,
большие.
здесь даже уже К маленькая.
Мгм.
Я палочку стараюсь. Окей, S is like twice larger than big K, yes?
Сейчас. Это...
Ну, мы все считаем, для S больше равно 2 в степени K плюс 1. Можно для меньшего, но это сложнее. And from this we see that this is negative, and moreover, it can be estimated like that. And from here we see that such series converges. Да? Потому что Q в минус 1 еще минус 6. So we see that let's denote by J of n, sum of Q1 to infinity S of Q converges absolutely. And also our difference, so here we have n to the power nu, yes? N to the power nu minus g of n is less than n to some small power, minus small power, yes? Because our series converges, and here is some positive number. So we see that r star of n is j of n plus b of n minus delta. J star of n, and also we know that j of n is less than 1. And later, I hope you will see that it has order 1. Okay. So now let us deal with this j star of n. And the idea is like that. First we so our j star, where is this? Here. We will expand our, but we will have integral from -1/2 up to 1/2, and the error will be small. So actually this integral is concentrated in the origin of 0. И главная часть вот как раз мы не считаем. For this we need some estimates for v of beta. And let me remind you that v of beta is our sum it's not again 8. Suppose that beta absolute value is less than 1/2, then v beta is less than minimum n to the power 1/k, which is actually become beta to the power 1 minus 1/k. Okay. First of all, some remarks. We want to estimate such sum 1/k minus 1. And this is m to the power 1/k plus b of 1. Again, because the integral of this is m to the power 1/k. Ну просто
Мы по R просто считаем.
Ну да, да, может не зачитаю. So first, what if beta is less than 1/n? Let's see. Yes, if beta, of course, we know that v of beta is less than n to the power 1/k, because this estimate. Да? Ну просто вот эта оценка, ну, то есть вот к этому применить, получится, что n степень однократная. Да?
What is big M?
Big M, да ничего, просто это, чтобы не n было, ну, переменная. This is true for every bcam. And if bcam then we have our sum, actually sum of absurd values, and our bound will be small n to the power 1 over k. Yes? So this is always true. And if beta is less than 1 over n, these two estimates, this is beta estimate, and this is true. Okay? So we may assume that so if this is true, then lemma follows. And now let us take bcam to be beta to the power minus 1. And terms of v beta, if m is less than bcam, what they contribute? They contribute not more than this amount. Yes? Do you have questions? Ну, еще раз, опять, применяем эту вот сумму, обрезали на бета в минус первую. Да? Обрезали. Какая оценка сверху получается? Бета в минус первой степени 1/4. Бета в степени минус 1/4. Ну, нас это устраивает. So we should evaluate some of our terms. Such sum n plus 1 n 1 over k n k minus 1 exponent of beta. And here we can integrate by parts, but also we can apply Dirichlet criterion or estimate. So here this is monotonic sequence. Yes, it's monotonically decrease. And this sequence is partial sums are bounded by bk of 1 over beta. And hence this is less than 1 over k m 1 over k minus 1 over beta. Do you understand how we get this estimate?
Да, можно пояснить.
Потому что у нас, когда сумма AN, BN, да, и, например, частичные суммы BN осциллируют, в смысле они ограничены, а AN монотонна, тогда мы можем, у нас есть оценка, что это меньше, чем AN монотонна там, AN в концах, и ограничение на верхней сумме BN.
Calculus first grade.
Да, это Дирихлей вот что придумал, типа записать это как разность, значит, AN разность, а BN частичная сумма, да? So this is, yes, very basic result. And these sums, partial sums, are bounded by this. And what we get from this is less than exactly beta to the power 1. Because n is beta to the power minus 1. And k is fixed. Let us remember this remark, this lemma. And now let j of n be integral from minus 1 over 2 up to 1 over 2 v beta to the power s exponent of minus beta n d beta. And the claim is that it's close to the previous integral. First, let's us evaluate all of this. It's less than integral from 0 to infinity, minimum. Minimum of what? Of this to the power s. Yes? N s over k beta minus s over k d beta. How to evaluate such integrals? So, if we are in the neighborhood of 0, then this second is very large, so we should evaluate it like integral n to the power s over k. So it will be integral from 0 up to, for example, n to the power minus 1, n to the power s over k d beta, plus integral from n to the power minus 1 to infinity, beta to the power minus s over k d beta. And first is n to the power s over k minus 1, and second is also as large. So this is our estimate.
Здесь, в какой степени в верхнем пределе интегрирования?
Где здесь? n минус 1. Ну, вот когда они как бы сравнялись, правда? Когда бета равно n минус 1, это одно и то же. So what's difference with J star and J of n? J star is you remember, yes? What's J star? It's such integral. Yes, not from 1 over 2, but from n to the power nu minus k. So this is less than integral from n to the power nu minus k up to infinity beta to the power minus s k d beta, and this is less than of course just computers. This is 1 minus s over k, and this is less. In terms of small n, we should divide everything by q. N yes, so we divide everything by with k, yes, and this will be minus 1 with some small nu. It will be s over k minus 1 minus some small number. Do you agree?
Where did nu go?
Ну, ню это 1/100, да? Ню умножить на это что-то отрицательное. Ну, вот что-то небольшое отрицательное оно и есть. Да? А остальное это как раз минус k это переворачивать, как раз s делить на k, минус 1 умножить на k. Вот. Okay, and so theorem, it will be theorem 2, including previous lecture, that our R of n, which is the number of representation, yes, all of this is if s is greater or equal than 2 to the power k plus 1. R of n is equal to j of n, g of n multiplied by j of n plus big O of n s over k minus 1 minus delta. Because we know that this is equal to j of, let me rewrite it, plus big O of n to the power minus delta of n plus bq of n so k minus 1 minus delta. It's like that. It's R star.
R star is when we integrate.
R star. We had R star.
In the beginning.
Все перемешалось немного.
Over big M, right?
Вот недавно же писали где-то сейчас.
R star is integrating over big
Вот.
M.
Значит, у нас было J со звездочкой, да?
Ну вот он это.
G of n у нас было вот так. Мы просто сделали сумму SQ и с от Q, где S от Q вот такое, да? Ну, теперь распространение на всю прямую. Так. А R star у нас было... Ну, вот оно было такое. Ну, вот мы... Вот это...
It's just integrating over big M, right? Big M cube.
Ну да. Да, мы его приблизили вот так. Вот это приблизили, распространили суммирование на все натуральные. Здесь там распространили на весь отрезок. Оценили остатки. У нас получилось такое. Also we know that this is less than n to the power s over k minus 1. Yes, and if we multiply by this, we get exactly this remaining term. And this is less than 1. So, and now, now we should compute this. So first, let us compute J. Theorem 3. We have half now. Yes?
Сейчас,
Да.
еще раз. Можете повторить
Мгм.
вот концовку второй теоремы, как мы доказывали? То есть мы просто говорим, что у нас R со звездочкой так, и потом каждый скобчик мы оцениваем как...
Ну вот мы приблизили, да, вот это J там, N там, вот так, да, это вот так приблизили. Но если мы раскроем скобки, вот это меньше единицы, поэтому вот это все дадут вот такой остаток. И вот это с этим тоже даст такой остаток. И еще такой же остаток из интеграла по minor x, да? Ну вот значит такое равенство. Okay, theorem 3. Suppose that s is greater than 2, then J of m is equal to gamma 1 plus 1 over k to the power s, gamma of s over k to the power minus 1, and of s over k minus 1 multiplied by 1 plus bq of n to the power minus 1 over k. So we can compute with some error term our sum. And for this we will need lemma 9, I think. Let alpha be greater than beta greater than 0, beta less than 1. Then sum from n plus n1 up to n minus 1, n to power beta minus 1, n minus n alpha minus 1. This is equal to n to the power beta plus alpha minus 1, gamma of beta, gamma of alpha, gamma of beta plus alpha, plus big O of n to the power minus beta. And it depends on alpha. how do you prove such lemma? Do you remember anything about beta function?
This is beta function, is it?
Yes. Yes.
That's all I remember about beta function. Or maybe something else, but
Please let me remind you.
it says something like
Beta, phi beta, we define like integral from 0 to 1, x alpha minus 1, 1 minus x, beta minus 1, dx. And we can compute it in terms of gamma function. It's gamma of alpha, gamma of beta over gamma alpha plus. I heard from some lecture that it's a bit similar to binomial coefficients formula, but I don't think so because for binomial coefficients you in denominator you have to product of two, and here it's inverse, but from this it's easy to remember. And
is there anything actually connecting binomial coefficient with beta function? Probably not.
yes, you can if beta and alpha are natural, you can open brackets and that's something. Yes, I can. So, and what's written in lemma 9, we just have sum, we relate it with integral, and integral is exactly like that. Okay?
Yeah, so we have to transform the sum into integral.
Yeah, sum. It will be integral over n from 0 to up to n. So let me prove this lemma. So we actually said how to prove it and how to deduce proof of theorem 3. Theorem 3. By induction, induction on S. So first let us note that J of n is Js. J of n that denotes Js of n, because it depends on S. It's such sum. Sum over such solution, m1 plus ms equals 1, k to the power minus s, m1 approach ms to the power 1 over k minus 1. And why is that? So this is our g of n, yes? And actually this integral is equal to the coefficient of exponent of beta n in if we open brackets here, yes? Да? Ну, если мы проинтегрируем, у нас все коэффициенты будут, ну, дадут 0, и вот здесь получится коэффициент при e от бета n, да, если мы откроем здесь скобки.
But it's also to the power of s there.
Да-да-да, и поэтому вот мы возводим степень s, да? Как, что такое v бета? Ну, это например, что он написал, да? Где мы? Давайте еще раз напишу, что v бета это this is sum up to n, 1 over k, 1 over k minus 1, exponent of beta n. This is such sum. If we take as power of it, a coefficient nth coefficient will be like that, sum over n1 and s, such that the sum is n of this. That's it. Вот. Okay. And so we have that J of n if s is equal to 2. When J of n if s is equal to 2, we have the sum exactly like in our lemma. Do you agree? So here is the sum, two sums with sum n, 1 to the power beta, another beta minus 1, another to the power alpha minus 1. And so in lemma 9 we should take alpha equal to beta equal to 1 over k, and this is exactly our sum in lemma 9. Okay? And from lemma 9, this is k to the power minus 2 and 2 over k minus 1, and here will be gamma 1 over k square, gamma 2k, 2 over k, plus b power of n minus k. But it's a bit different answer, yes? So what we want, yes, and we can group, so what's this? To square, it's square of 1 plus 1 over k square, yes, because of that, you know that x gamma x is gamma x plus 1. Okay, and this is exactly the claim of our theorem in case s is 2. And otherwise, js plus 1 of n is, we can write it like that. One over k, m 1 over k minus 1, j s n minus n. Do you agree? Ну, мы одно из слагаемых и однократную, и одно из, например, m1 выделили отдельно, и остальное рассмотрели. And then we can, by induction, apply our lemma. For j of s we already know, and when we again apply our lemma, because we are in the case of lemma 9. Yes? Да? Потому что, ну, то, что теорема утверждает, so the theorem claims that we have here n to the power s over k minus 1. So here will be n minus m to the power s over k minus 1, and we sum this over m, and this is exactly lemma 9, which let us to compute. Let me not finish. I don't want to finish this, okay? But you see that by induction, actually, we can compute this. Now let us discuss. So we computed our sum, and we see that it's j of n is a constant multiplied by n to the power s over k minus 1, and that's what we wanted, yes? Да, давайте еще раз посмотрим на выражение. Вот g of n, ну, g от n это будет константа какая-то, да, мы оценим как снизу сверху, а g от n растет как n степени s делить на k минус 1, ну, тоже константа вот какая-то выскакивает. Что ж такое? Okay, now let us compute j of n. Let me write it again. That's all what remains to compute. So this is our sum. This is S of Q. And SQA is like that. I write it again. It's analog of Gauss sum. Lemma 10. Actually, yes, lemma 10. Says that what I want to prove that SQ is multiplicative function. Okay. S of Q is multiplicative function. So first, if Q
Like absolutely multiplicative or
not absolutely like
co-prime.
yes, for co-prime. Then S Q R is B Q is equal to S Q A S R B. And the proof of this lemma 10, it's just Chinese Chinese.
Сейчас нам пишется.
Есть теорема
У
Баста.
нас УР или КУВ взаимно просто.
У и R взаимно просто и вот
Мгм.
попарно. So it's because SQR AR plus BQ is equal to. If you want, I can just it can be exercised for you because it's it's okay, I will write. So let me write it first, and when we discuss over Q plus KQ to K over R, and here I took M is equal to CR plus BK. So our S, well, again, we don't see our, where is our big S? Here it is. So every M modulo Q, yes, with the sum depends only on, this depends only on M modulo Q. So if T runs from 1 up to Q, U runs from 1 up to R, this sum runs over all residues modulo QR. Согласны? And then M to the power K so we have M to the power K, we multiply it by A over Q plus B over R. Yes? Here is we multiply by A over Q. In our case, we will multiply by AR plus BQ over QR, and this is such sum. And M is T plus UQ, and if we open brackets, and if we remember that exponent of natural number is 1, we will get such sum. Согласны? Потому что если мы возьмем слагаемых там хоть одну Q есть, то вот с этим уже можно не считать. Да?
Сейчас еще раз. Мы что сделали? Мы вот просто можете объяснить, пожалуйста, что мы именно домножили?
Ну вот наша сумма, вот эта,
Да.
это сумма по всем n вот такого. Да? Ну, где такого. Если мы m в степени k раскроем скобки, там будут, и там есть, например, слагаемые, которые и Q, и на Q, и на R
Да,
делятся,
понятно,
то
понятно.
они везде, ну, целые числа будут.
Да,
Поэтому
всё,
вот
хорошо,
только вот
понятно.
это остается. And here, this is exactly product, this product. Yes? Because again, for any fixed star, this runs for overall residues, modulo Q. Lemma SQ is multiplicative. Multiplicative. Because SQR, let me write it in such way, and you will see. Where is our definition of S? Вот здесь. Правильно, вот здесь. So, this is SQ. And if you write SQR, we will get such sequence, and here AR plus BQ, as in the previous case, it's runs overall residues modulo QR. And now we just apply our multiplicator with this is product, and we get that this is S of Q, S of R. Also, S of Q is real. Is real. How do we see it? I think if we change A to minus A, this sum does not change. Yes, because here we have symmetry, modulo Q, A and minus A. And hence we have such theorem 4. If S is greater than 2 K plus 1. Let us divide. Yes. As it is multiplicative. Oh, no.
Просто можно обвести область, и она все будет.
Да, я так хотел, но тут что-то не то. Yes, as it is multiplicative, let us denote T of P, sum of each from 0 to infinity, as P to the power H. Okay, and now we know that, it will be theorem 4, that T of P converges absolutely. Yet, because we know that S with sequence converges absolutely over all natural numbers. Yes, we G of n is product of t of p over primes. Moreover, there exists some number such that our product of all primes greater than c, t of p is close to 1. So we already proved this theorem. The last follows from again from convergence. So we don't have a lot of time to let me just prove the last lemma. So let us denote. I want to say that this T of P has some good meaning in terms of representations of our number modulo P in a sum of powers. Let us denote Mn of Q, number of solutions of 1 to the power k plus ms to the power k with solutions modulo Q. And lemma plus lemma is that sum d divides q, s of d is q to the power 1 minus s mn q. And so from here it follows that t of p is such limit. L tends to infinity, p to the power L s minus 1 mn of p to the power L. Okay, so it's just number of solutions modulo p to the power A multiplied by some power of p, and yes, here of course it's a mistake, sorry, it's 1 minus s, because number of solution grows and this number should decrease. 1 minus s. And how to do you see why from the first part of lemma the second part follows? T of p is the sum of s over powers of p.
У нас получается,
Ну
если
да.
мы возьмем q простым,
Ну, куб по степени возьмем.
ну
У
да,
нас вот такой получится, да?
да.
Ну, все. Так. Да, ну. Okay, now I prove lemma. It's just what's the man of q? We can write it like that: 1 over q, sum 1 up to q, sum m1 ms equal to 1 to q, r m1 power k plus ms to the power k minus n over q. See, if this is 0 modulo q, every term is 1, and if it's sum over r, and we get 1, yes? And if it's not 0, this sum over R is 0. Yes, just finite Fourier transform, we can say. And now let us take D to be Q over greatest common divisor of R and Q. When this is equal to 1 over Q, sum over D divides Q. So we just R over Q, if we are not co-prime, we just divide it by the greatest common divisor. And we will get such sum. A is co-prime to D, Q over D to the power S, because we have like the same sum. So R over Q is fixed when we have Q over D to power S, to Q over D possibilities for it. And here will be, yes, and M also we run from 1 up to D. Plus MS K minus N over D. And we know that S of D is D to the power minus S. D is 1. S Q A to the power S minus A N over D. Okay, just we write it our Mn of what? Of Q in such like that, and when we looked at we regrouped our sum such way that greatest common divisor of R and Q is fixed. And when we look at it and we see that it's exactly S of D multiplied by Q to the power S minus 1. Okay, let me stop here. Of course, it's not finished proof, but let me say in words what we want to do. First of all, I claim that this sequence, we have limit here, yes? Actually, this sequence stabilizes. То есть слагаемое перестает меняться с какого-то момента. Вот. Может, я, кстати, не прав. Why this stabilizes? Because if we have some solution, what is M? Yes, it's number of such solutions. Modulo some power of P. From this solution, we can get a solution modulo power of P to power L plus 1. How you will do this? Do you know? Ну как из решения там, по модулю 2, там 3 в 9 получить решение по модулю 3 в 10.
Ну просто там множить.
Нет, изменить вот там m1 плюс что-то умноженное на p в какой-то степени.
Да.
И там получится линейное уравнение. So from any solution we have we can continue to a solution modulo p to the power L plus 1, and in such way we can continue to a solution in periodic numbers, and step by step. And why there are p to the power s minus 1, yes, possibility. So this is multiplied by p to the power s minus 1, this multiplied by p to the power 1 minus s, if we decrease L by 1. Because we take p to the power s minus 1, like we can take m2 to be old m2 plus some p to the power, I don't know, maybe to the power L, I think, yes? Or, yes, L. And here will be some number modulo P, yes? And for any M2, etc. ms, we can take this A to be arbitrary number modulo P. And for M1, for example, we have only one possibility. Да? Ну, то есть мы продолжать можем как? Мы для M2 и так далее MS мы там подбираем любой коэффициент, какие хотим, а для M1 ну, там будет только, ну, одна возможность, что ну, сумма должна 0 равняться. Okay, and as this stabilizes, we just want to prove that it's not zero to finish our theorem, yes? Because in this way we will get our and how to prove that this is not zero, we need to show that this has the non-trivial solution modulo some power of prime. So we need to solve one problem modulo powers of prime. And this is much easier. Okay. Ну, понятно, то есть мы свели задачу к тому, что оно представимо в виде какой-то степени S по модулю там простого. Ну, там, или
ну да, и теперь нам нужно для степени простых все сделать для помощи.
Ну да, да. А там, ну, там как-то можно, только раз проще, конечно. Ну, вот.